in figure 9.4, there's a lot of things going on here. I want to point out a couple of things and relate them to something that we learned, that we went over already in Chapter 8. What you see in these two graphs are two different kinds of soil. First we have a mineral soil, a regular mineral soil you could say, and then we have an organic soil. And remember that organic soils can actually have a change in the amount of CEC available, the ability of that soil to exchange cations on its surface. We can have a change in the CEC based on the pH. And so what this graph is showing, this line here, this effective cation exchange capacity, and we'll highlight this in blue here, this effective cation exchange capacity here, that's the actual cation exchange capacity that we can see on a soil. And you'll notice that this pH, there's two types of charges you can have, a permanent charge and a pH dependent charge. A permanent charge is based on the mineralogy of the substance, in the case of the one on top, the mineral soil on top. But in the case of an organic soil, so you can see the real large swing here in if we're at a high pH, so we're here at pH 8, we have quite a high effective CEC. If we have a low pH right here, we have a very low effective CEC. And I wanted to bring to your attention why that's the case. Why would the pH change? Or sorry, why would the ability of a soil to hold cations change just based on the pH? So let me bring up this picture here to help us sort of figure that out. So in this picture, this is organic matter. Okay, so this is a molecule of organic matter here, or not a molecule, like a colloid of organic matter here. And it's in this particular graph. This is figure 8.9. In this particular graph, it's just pointing out the different kinds of groups that can exist on organic matter. But the important thing I want you to see is the relationship of the charge to the hydrogens on this. So right there is a hydrogen. Here is a hydrogen. And so if we've got a low pH and we've got a lot of hydrogens, all of a sudden these charges over here that are negative, they become OHs. So you have an OH here, an OH, an OH, an OH. Okay, so now what was negative now is neutral. It doesn't have a negative charge anymore because there's so many hydrogens floating around in that soil solution, and they have gone on to those negatively charged sites on the organic matter, that now we have a soil, if it has a lot of organic matter like we see over here, a soil that as the pH goes down has less ability to exchange cations because hydrogens are filling up those quote-unquote abilities, filling up those places, those negatively charged sites. But then again, if we increase that pH, all of a sudden we start to lose hydrogen ions. We lose hydrogen ions, and we gain this negative. We gain that negative charge back because hydrogen ions are being consumed, and they're actually coming off of these hydroxyl groups into the soil solution and getting consumed. So that's the way you can see again, that's this pH dependent charge right here. It depends on the pH as to how many of these slots are going to be open, how many of those hydroxyl groups are going to be open or not open.